So if I remember correctly, we had sum n equals 0 to infinity of 2x, was it minus 5 to the n? 2x plus 3 to the n over n? Okay. All right. We're looking at this power series, and I was asking you about its convergence, and we did not get an opportunity to run the ratio test on it, right? So let's run a quick ratio test on this. And the ratio test, I don't know why it's doing that. What I'm going to do is plug in n plus 1 into this, right? And then divide that by just that. And so when I plug in n plus 1, 2x plus 3 to the n plus 1 over n plus 1. But then I divide this by this, so then it flips up, right? Flips, and I'm going to go ahead and start doing that flipping as my first step. And remember, what we want is for this to be less than 1. Why do we want that to be less than 1? Because that's what the ratio test tells us, right? If that's less than 1, then it's going to converge. So now what I'll do, and again, just kind of in an effort to save a little bit of time, I don't know what it is. Let's rewrite this right here as 2x plus 3 to the n times 2x plus 3 to the first power. Do you all agree that that's what that is? Yeah? The n plus 1, I can split it into 2. The reason I do that is so I can cancel this out. And now what we'll do is we'll take a look at this limit. Whoa. And I'm going to have some stuff in here that has n's, and it appears I also have some stuff in there that has x's, right? So let me get the n stuff first. N over n plus 1. It's going to start to drive us all crazy here in a second. Don't think it's this connection.
What's the projector?
Yeah, I think it's the actual wiring that goes from there into the wall. We've had a lot of problems with these wall plates. Apparently they're like $800 wall plates that fall when, or break when you breathe on them. Okay, so, all right, that times, what's still in here? 2x plus 3, so let's put that in parentheses. Now remember, the 2x plus 3 is going to behave here as if it's fixed. It's not really moving, right? But the n is going to go to infinity. So what does this go to as we go to infinity? What does this go to? Infinity over infinity. So if we ran a quick L'Hopital, we get 1/2. Wait, 1/2, sorry. We get what? 1, right? We get 1. That means that as n goes to infinity, this whole expression really turns into the absolute value of 2x plus 3 is less than 1. Right? That's what that turns into. So that's what we would need in order for this thing to converge, right? So we talked a little bit about how to mess with these, right? Do you remember how we can rewrite this so that we don't have the absolute value anymore?
Yeah. Put the -1.
You put -1 on this side, right? So you're going to squeeze it between -1 and 1, and then on the inside you put 2x plus 3. And then you solve this for x by first subtracting 3 on both sides. So what happens if you subtract 3 on both sides? You get -4 is less than x, 2x, sorry, which is less than -2. And then divide everything by 2. So we'll have -2 less than x less than -1. Okay, so I'm thinking maybe I'm just going to turn off the projector. me just try this. I'm going to disconnect this one time. And I'm going to kind of kick it over here, kick it, and then put it back in and see.
I think the kicking is what, like.
The kicking probably is going to fix it, yes. All right, so let's try and recap what this all means. If we were to be looking at this as a function, right? If we were to be looking at this power series as a function of x, then what we've found so far is that the domain of this is -2 to -1. Would you agree with that? I can plug numbers between -2 and -1 into that, and it will spit out answers. However, we're not done, because the ratio test tells us what happens in terms of convergence and divergence, but there are times when the ratio test fails. When would the ratio test fail? When it equals 1, right? So I actually need to take that into account here. We know so far that if the absolute value of 2x plus 3 was less than 1, then that meant we had convergence, right? Convergence. If the absolute value of 2x plus 3 is greater than 1, we have divergence. What we don't know is what happens when the absolute value of 2x plus 3 is equal to 1. Do you understand that? So we need to now take a look at this and investigate this a little bit further. So this domain right now, I'm putting a question mark next to it because I'm not quite sure if that's everything. So taking that last inequality, or last absolute value equation, when we solve this, right, this is basically the same as saying, when does the absolute value, so think about the inequality we just had, right? Maybe you can tell by our answer. What happens when -2 is plugged in? If I actually plug in -2, which this says I'm not allowed to, right? If I plug in -2 right here, then I get -4 plus 3, which is -1, which is 1, absolute value. And if I plug in -1, I get 2 times -1, which is -2 plus 3 is 1, absolute value of 1 is 1. So it looks like the two values that are going to make this thing equal 1 happen to be these two endpoints, right? So you actually don't need to solve that as long as you understand that the solutions will come from these two. You with me so far? So our question remains, what happens to this power series if x is equal to -2? And what happens to this power series if x is -1? So that's what I'm about to figure out. What happens at x equals -2 and x equals -1? So let's start with -2, because it appears on the left side as we move from left to right on the number line. So I'm going to go ahead and just let x be equal to -2. And when I say that, I'm fixing x. Go ahead and rewrite the series. What would that series be if I rewrote that and replaced x with -2? So we would have -4 here, plus 3, that's -1 to the n. And over n. Agree? And now we're actually back in Chapter 8, Section 4, where we're just looking at a series, and we just want to know if it converges or diverges. So how would you check for convergence or divergence of this one? Okay, so that's always the first one, right? N-term test. So if we let n go to infinity here we'll get 0, won't we? Which tells us nothing, right? What? Alternating series test. This is an alternating series, right? Why don't we run the alternating series test on it real quick? So I'm going to do an alternating series test. the two things that we have to show for an alternating series are first that it's decreasing, right? And what we're really investigating here, if you go back to alternating series, the positive part of the alternating series is what we call the A sub n. You can look off your cheat sheet on alternating series test. It's the positive part of it that's the A sub n, and we want to make sure it's decreasing. So I want to show that A sub n plus 1 is bigger than A sub n. That's what it means to decrease. So is this true? Plug n plus 1 into there. Is that bigger than this? What did I? Oh, I did it wrong. Thank you. The nth one's bigger than the n plus 1, right? This one to the left is bigger than the one to the right, and they keep getting smaller. All right. My apologies. My apologies. Now, is that, we were going to have trouble right away because that wasn't going to work, but yes? That true? You could cross multiply and check this? That's true. So it decreases. Now what's the next thing we need? The limit as n goes to infinity of a sub n, which for us is 1 over n. We need that to go to 0, right? And it does. What does this mean? Converges. We've satisfied both conditions of the alternating series test. Therefore, it converges. So that means in the big picture now, going back to the original problem, right, f of x, we were asking ourselves, where does this converge or diverge? We knew it was between -2 and -1, right? We knew it was between -2 and -1, but we weren't sure at -2 what was happening. We checked at -2 and we see that it converged. That means that this is not technically correct yet. I need to include -2, right? But I also need to check -1. So let's check -1 now, all right? Let x be -1. Rewrite the series. Rewrite the series, replacing x with -1 in here. 2 times -1, -2, plus 3, that's just 1, right? 1 to any power. It's just 1, right? So isn't the top just 1? I don't have the alternating anymore. And over n, this is harmonic. What do harmonic series do? Diverge. So it diverges. That means that at -1, if I try and plug that into this function, I'm going to get divergence, which means I don't want -1 in there, right? So my final answer now is this. This series right here, this converges on the interval -2 with a bracket, -1 with a parenthesis. And in terms of a number line, thinking about it in terms of a domain, what you're saying is that you can plug anything in between -2 and -1 in. You can plug -2 in, but you may not plug -1 in. That's your interval of convergence. See, it's an interval where it converges. We good? Yeah. Yes.
For like, I know like the 1 over n was always harmonic, but does it matter if n equals 0?
Hold on. I just wrote that down wrong. You know what? I think I wrote the problem down initially wrong. Yeah, I wrote it down initially wrong. It had to start at 1 from last class, because it wouldn't have been defined at 0. That was my fault. Maybe did I write it down with 1 last class, or 0? I did 0. Okay, that was an oversight on my part. So yeah, we would want this to start at 1. I'm glad you caught that, because that's one of those things I go back and watch it later, and I'm like, what the heck? All right. So we have, I know last class was a long time ago, but let's take a look at the last 3 examples that I've done. Okay? So I'm going to ask you to look back in your notes here. The one we did before this, I believe, was the Bessel function. Is that correct? And the one before that was something else. I don't remember what it was.
It was n factorial.
N factorial times x to the n? Okay. Yeah, now I remember. All right, so I think we had this. N factorial x to the n. And then the second one that we did was the Bessel function, right? Bessel function. And then the one we just did, which was the -1 to the, no, 2x plus 3 to the n over n, right? So let's just compare these three, because there's a reason why I gave us these three problems. Do you remember where the first one converged? What did we say at in your notes? Where did this one converge? At x had to be 0, right? Where did this one converge?
Part.
Where did the Bessel function converge? What was its interval of convergence? Where was it defined? All real numbers. So we have like -infinity to infinity, right? And then this one we just found was -2 to -1, right? So if we look at this graphically, number line 0, this one only converged at a single point. This one, number line, converged both directions forever. And this one converged on this interval, like this, right? 3 examples. And the reason why I gave you these 3 examples is because we actually have a theorem, which I'm about to put on the board, that tells us for any power series, you're going to get one of these 3 results. And there's no other possibility. You're either going to get convergence at a single point, you're going to get convergence everywhere, or you're going to get convergence on an interval. There's no fourth option. Okay? So that's the following theorem. That's right. A power series cannot diverge everywhere. It must converge at least a single point. Right? You're guaranteed at least one point where the power series will converge. So here's the theorem. Given a general power series, and I hope that you remember that this is the actual formula for a general power series. Then one of the 3, or one of these, must happen. First, and let me go make sure I use the same order that the book does. I think we're going to do the point first. Where'd it go? Yeah. Okay. It converges at x equals a only. Two, it converges for all x, which means from -infinity to infinity. And the third possibility is a little more complicated, all right? So it's going to take me a while to kind of explain the third one. The third one, it converges on an interval. Now, that seems pretty simple, but I need to explain a couple of things about this interval. The interval that it converges on could be an open interval, So fill in the blanks here with any number, right? A number here, a number here. But what do the two parentheses mean? Do not include those numbers, right? That could happen. Or you could have maybe, like we just had, include the left but not the right. What other possibilities do you think